Welcome to our poster, 2D sulphonated azopolymer, kinetic evaluation of crystal violet adsorption. In recent decades, porous materials have been a trend in materials science, due to their great versatility, geometric structure, defined pore size, and large surface area. These characteristics make them suitable for a wide variety of applications such as water desalination and others. Moreover, these compounds have the ability to capture dyes in wastewater. Therefore, they can be used as a tool to prevent and restore the damage to the environment and the toxicity caused by exposure to dyes. These materials can be manufactured from organic and inorganic precursors, among which can be mentioned mesoporous silica, mesoporous carbon, metal organic frameworks, covalent organic frameworks, and porous organic polymers. In this work, a sulphonated azopolymer was synthesized and its adsorption kinetic behavior was evaluated using crystal violet. The sulphonated azopolymer was synthesized from 4,4-diamino-2,2-stilbenedisulfonic acid by adding it to water with a portion of concentrated hydrochloric acid to make the solution acidic. An aqueous sodium nitrite solution was added to the acid solution to get the diazonium salts. Then a fluoroglucinol basic solution was added to the flask with the diazonium salts. Thereafter, the azopolymer was synthesized and it was left at room temperature to evaporate the water and filtrated with vacuum. The azopolymer was characterized by infrared. The adsorption kinetics of crystal violet on the porous material were tested in a 100 ml flask containing a crystal violet solution. In each experiment, different initial concentrations were used. The azopolymer was aggregated to the crystal violet solution and all experiments were carried out at 25 degrees Celsius, initial pH 7.0, an agitation rate of 600 revolutions per minute. The pseudo-first order, intraparticle diffusion, and Elovich kinetic models were used to describe the adsorption process, according to equations 1, 2, and 3, respectively.
Here we present the pore structure of synthesized azopolymer with adsorbed crystal violet, as well as the spectra obtained in the infrared characterization where the respective bands of the functional groups in the structure can be seen. The following graphics the results of the adsorption kinetics experiments according to different models are represented. 1. Pseudo-first-order adsorption. 2. Elovich adsorption kinetics. And 3. Intraparticle diffusion adsorption kinetics of crystal violet on sulphonated azopolymer. Subsequently, a table where you can see the expected results according to the model and the experimental results, as well as the values of the correlation coefficients. A computational evaluation was also performed to calculate the binding energy. For this, the pore of the azopolymer and the violet crystal were modeled and a docking between these two compounds was carried out with autodock vena. From the resulting complex, the interacting part was isolated and its geometry was optimized using density functional theory in ORCA and the single-point energy was obtained. Subsequently, the structures were separated leaving a distance of 100 Armstrongs between them and the energy was calculated again. Then the subtraction of the two energies was used to have an approximation of the adsorption free energy of 5 kilocalories per mole.
Conclusions. The synthesis of a new sulphonated azopolymer with adsorbent capacity for crystal violet was achieved. The material is capable of adsorbing up to 21 mg per gram of crystal violet onto the polymer. Crystal violet interaction with the polymeric material is favorable with a computational free energy of -5.16 kilocalories per mole. The pseudo-first-order kinetic model fits well in the first 30 minutes. Showing a decrease in the constant as the concentration of the system increases. The Elovich model shows that alpha decreases from 0.544 to 0.131 mg per gram min, which indicates that the initial adsorption decreases when the concentration of the system increases. The intraparticle diffusion model, IPD, tells us that the intraparticle diffusion speed decreases as the concentration increases, assuming a greater layer of resistance on the surface. The IPD model also shows us that the adsorption